let us move into the next module, that is adiabatic switching, or I can say adiabatic circuit. Now we want to know what you have studied in the previous lectures. So whatever the previous classes and all we have studied, how it will be compared or how it will be different from the previous modules or previous topics, we can say. In the previous topics and all what we studied the static. Previously we have studied static CMOS circuits. Static CMOS circuits, or as we know that has many advantages, like such as low power dissipation and the reliable operation, and it will be availability for the computer aided design. So in this also we have seen that all the circuit nodes will make a rail to rail, that is the transition from 0 to VDD for each switching event, and the supply voltage VDD will be remain constant actually. But this consequence, the output node in the static circuits, how it will be in the sense like the output node will make a transition from 0 to VDD with the load capacitance, that is CL actually. So because you might have seen the circuit was like this. This will be your PMOS network. This will be your NMOS network. Then the input will be given over there. This will be your VDD. This is a general circuit of static CMOS circuit. This will be VSS, and here in the output there will be a no capacitance. Right, as we know that. So now as we know that the output will make a transition from 0 to VDD with the load capacitance CL. So now in that we found already the energy, how much the energy will be there, that is CLL into the VDD square. This is was the energy will be drawn from the power supply. So out of this we see this will be the energy will be drawn from the power supply, but how much it will be stored? It will be stored how much this is drawn from the power supply, right? The energy drawn from the supply is this much, but how much stored? Is any answer? How much it is stored actually? Because when input is equal to 0, the PMOS will be on, it will be drawn, right? How much will be drawn from CL into VDD square actually. But how much will be stored in the sense, like the half of the energy only will be stored. That is, E will be equal to 1 by 2 CL VDD square. This much energy only will be stored. This already we must have studied. This much energy will be stored in the capacitor, and the remaining half of the energy will be dissipated in the PMOS itself network. So subsequently, when the output node, this will be like from 0 to VDD. Okay. Now when I go for a VDD to 0, what will happen? The energy that was stored in the capacitor will be dissipated to the ground via NMOS network. So here very important thing is here the power dissipation will take place because of switching event. The switching event is converted to heat. That is the main reason here actually. So you can say the main reason is switching event is converted to heat. And the switching event is converted into heat. So which ultimately we can release to the environment actually, because it is dissipating the power. Right? It's dissipating the power, we can say. So what we have to do for this? So we need to reduce the power dissipation. So what the circuit designers and all they did, they will reduce the one was to reduce power dissipation. They reduce the power dissipation. So what are the techniques they use? They can reduce the supply voltage. This is we studied. Then they can decrease the node capacitance. Decrease the node capacitance or minimize the switching events. So these are the things only we studied in the previous topics or the previous lessons. So now here there is a novel approach here. There's a novel approach here to achieve the energy dissipation below the limit, because as previously as we've seen, the power dissipation will not go beyond this. In the sense less than 1 by 2 CLVD square, the power dissipation will not go beyond that point if I use the previous techniques. Still, if we want to reduce less than that, the sense beyond, so not 1 by 2, beyond CLVD square actually. So the novel approach is, what is this approach I said here? This approach is to achieve energy dissipation below this lower limit. In the sense limit of CL VDD square. See, this is what very important. So how it can be done? This can be done with the help of the new class of circuit. That circuit only is known as adiabatic circuit. So now this adiabatic, so here we need to know what is this adiabatic is a refers. The term which is given here, that's a new term, like kind of the new term, right? What is this adiabatic? The adiabatic is nothing but the refers, it's a thermodynamic process. Thermodynamic process that exchange no heat with the environment. That is very important. So, or otherwise we can say in electronic wise, if you want to say, this is in a mechanical term, it is like a, we given terms of with electronics, right? So else I can say in electronics way, a system without power losses. That is the meaning in with respect to electronics. This way, if I want to say, it's like a system without power losses. There will be power loss will be there, but without power loss in the sense, so it's like as I mentioned earlier, it's a reversible logic. That is the main important logic we are going to perform over here. So to study that, so here thing like very important thing I'll say here. So as I mentioned earlier, so some of the points we noted here you can see the full swing voltage mode, the CMOS logic sites have been extremely successful for both the technically and the market shall live with that. So the switching power dissipation as I mentioned earlier, the CMOS circuit with the capacity load as lower limit of CL square by 2. Now as we mentioned next, the adiabatic switching circuit, the switching power, the dissipation below this lower limit. So this term, okay, so the reduction of power dissipation will occur at the cost of slower speed of operation actually. So they're very important, that is why I mentioned here. It also allows the recycling of energy to reduce the total energy drawn from the power source. That is a recycling, that is a reversible logic we are going to do. So this is example as I mentioned here. This is what the switching power dissipation due to the charging and the discharging of a load and a parasitic capacitance. So here it is a simpler circuit which has in this if your pull up network is on and pull out is on, then it will be the charging current will be there, this will be charged over there. So that is why here we said the dissipation, the power dissipation will be calculated, or as we discussed in the previous classes, the power dissipation will be happened with the following factors like this alpha naught is nothing but the switching activity factor, then CL is nothing but load capacitance, VD is power supply, F is nothing but your clock frequency. Then here plus the summation means this will be your CL, right, the load capacitance. Then there will be some, the parasitic capacitance will be there. Where is the parasitic capacitance? Like the node capacitance you can say. So that combination. So the sum of the node capacitance and the load capacitance will provide a power dissipation. This is what previously we studied in the switching power dissipation. We studied the previous cases and all. Now what we will do, let us go for the simple thing is like conventional charging. Let us see the conventional charging. And since what we are going to see, let us take a simple example. Conventional charging, a diagram like just like the resistor, then here one capacitor will be there. I'll connect to VSS. Then here we are going to keep the supply voltage, that is plus minus. So we are going to apply here that side like this, right? So now this is from 0 to VDD. So I can say this will be your resistance, this will be a CS. So here we are going to take a output in Vout here. So example, this is a Vout. Now we can say what will be here the time. So now I can say at t is equal to 0. At a time t is equal to 0 means at a time 0 the input voltage is 0 in the sense the capacitor initially it won't charge. At time 0 the capacitance won't charge, right? Initially no charge in the capacitance. No charge in the capacitor initially. Okay, so how it will be in the sense now when the time increases, in the sense at time t is I mentioned, right? So we now we are increasing the VDD now. Slowly we are increasing. How it will be there? The diagram will come like this. Say example, this is the diagram, right? You can consider this diagram. This will be is equal to t. Then this will be your Vout, because we have to get the Vout. V naught or Vout of t with respect to t. Now as the time t increases, what will happen? Then means you are gradually you are increasing the VDD, or just you are applying to VDD. When applying this means your capacitor start to charges. Capacitor start to charges in the sense I can say the capacitor will be start to charges at one particular point of time. It will be constant like this, right? So this is, I can say, V out of t is greater than 0. At the time t is equal to 0, the V out is equal to 0, I can say. Right? At t is greater than 0, so what I will get now will be is equal to the capacitor start to charges. Now it is like it's going as like exponentially growth is going. So now we can say the V out of t is greater than d is nothing but VDD into 1 minus e to the power minus t by RC. Where here you can see this is the thing you apply here. When t is equal to 0, then V out will be 0. When t is equal to 1, that is gradually increase, automatically the capacitor start to charge. This is the expression we will get. Now here we didn't found or we didn't check with the current actually, because the same just we said at time t is equal to 0, the this is. So now what we'll do, let us go with with respect to current actually. With respect to current we'll go. So now what we'll do, let me put here, here is in. So now let us, so the current is nothing but I of t. Current. Let us find out how it will be current actually. This is about the voltage. Now what about the current actually here? So let me say after t is equal to 0, the current will be starts flow. Initially time is equal to 0, the capacitor does not have any charge, and therefore the voltage across the capacitor will be 0. That is what we see already. Then the current flow, how much the current flow? So simple, I can say I of t is equal to, the current is flowing, right? I of t is equal to, from the circuit, what is the current actually? I of t is equal to, I can say the current is flowing like I can say R between and this to this. So I is equal to P by R. So as we know that this is nothing but VDD minus V out of T divided by R. So this is, as already we know what is your V out, because this is for at t is greater than 0 only, there will be some amount of current will flow actually. So t is greater than 0. So VDD minus V out of t is equal to VDD into 1 minus e to the power minus t by RC. So substitute this over here. So we'll get VDD minus VDD into 1 minus e to the power t by RC divided by R. Now we can simplify this. When you simplify this, what will get? So we'll get us VDD by R into e to the power minus t by RC will get. This is nothing but your I of t. So we can say how this the graph will be there now. I of t graph. So let me put a graph. This will be your t. This will be your I of t. Yes, so what is I of t? The I of t is nothing but VDD by R. The maximum is this amplitude, right? The current, maximum current is VDD by R. You can see e to the power minus t by RC. E power 0, when t is equal to 0, this is the maximum value I will get. When t is equal to 1, 2, great increasing, so what will happen? Exponentially decaying. This will be exponentially decaying. Right? So it's exponentially decaying like this we get. So now you can compare that graph and this graph. So from this what you will do, you will calculate the power now. When you are calculating the power, that is P of t. What is P of t? P of t is equal to I square of t into R. What is the I square t? I of t already we know. Then I square t is nothing but it is VDD by R into e to the power t by RC, the whole square into R. Now what will be this? This will be VDD square by R square into e to the power minus 2t by RC into R. The R will get cancelled. Then finally I will get us, this is will be your file, right? So it like a VDD square by R e to the power minus 2t by RC. This will be your power actually. So now let us see what will be the energy dissipation. The energy dissipation. So let us see the energy dissipation. Energy dissipation is nothing. This is power. Power is like it's a finite, right? So energy dissipation is infinite actually. So 0 to infinity P of t into dt. That is the energy dissipation. Finding the formula. So it is how much? 0 to infinity. P of t is nothing but VDD square by R into e to the power minus 2 by RC into dt. So this is independent, it is not dependent on t. VDD square by R is taken outside of the interval infinity e to the power minus 2t by RC into dt. So now what will be this? Will be is equal to VDD square by R, integrate that, will get us, what will be this? Will get us minus RC by 2 into e to the power minus 2t by RC, limit, apply the limit. When I apply the limit, finally I will get as 1 by 2 CL into, that is C, okay, C into VDD square. That is C is nothing but your load capacitance. That is why RCL I can say. Simple. As per this circuit, I can say CL into energy dissipation. Now, from this, we can make an observation. What is the observation we can make from this now? The energy is dissipated to charge a capacitor is dependent of R or independent of R. Energy dissipated to charge a capacitor is independent to R or dependent to R? It's a independent of resistor. This is the one of the very important. See, in your circuit I am having a resistor R, but even though if I use that resistance R, it is not affected. It's independent of your energy dissipation. Is independent to charge. When the energy dissipation to charge a capacitor is not dependent on resistor R. So that is a very important thing in your circuit action, because as you know that, so this is the we have to make a very thorough important point about that. That is why here we see this diagrams and all we are showing here. See, for the charging, these two graphs here actually we done. This is about your voltage, this is about your Q charge graph. So same, like what is the graph we run, the same similar kind of the graph only. This will be your current, this will be your charge actually. So adiabatic charging, this is whatever we are saying, it's a adiabatic charging. So here we are using the source, that is nothing but the current source is nothing but it's a time dependent current source. Which one? The source is time dependent current source actually. So this only will be used, that is I of t only is used to charge the capacitance C. So this circuit will be used to the model a CMOS circuit with the output resistance to drive the capacity load. So this is what we have seen, but similarly even here also we have seen the same similarly circuit. See, like VC of C in the sense, this is the simple concept I have shown about like energy dissipation is independent of R. So now we can see the adiabatic charging. This is conventional charging. Whatever we shown, This is your conventional charging. That's the conventional charging. This, as I mentioned here, normally how what will happen at a time t is equal to 0. The switch, this switch is something you just you think this is one switch. When time in t is equal to 0, it's an open switch. The capacitor will not be charged. When the charging will be progress, the current decreases and the charge will be increases. Means when time is t is greater than 0, the current will be decreases and the charge will be increases, because as we've seen here previously, VDD by R actually, correct. So because here this VDD minus the V out by R, so here we see no the parameter, see here I of t VDD by R. So what happened, as the charges increases, that is greater than t is greater than 0, as the charge is increases, I can say the I of t will be decreases. That is, your current will get decrease. So that is why here we written the Vc of t, the voltage across the capacitance, the function of the time, the Vc or V0 of t also I can say. Vc will be like a 1 by C into I of t. Then the average current will be I of t will be is equal to C into Vc of t by t, the average current. Then here we found the energy dissipation in R. So now what we will do, like so let us go for the adiabatic charging here. In the adiabatic charging only, just here we found the averaging current from 0 to t. Then the energy dissipation in R, the energy dissipation in resistance from 0 to t will be equal to t will be given by the energy dissipation, that is R into 0 to t I square dt will be is equal to R into I square of t, where the small t will be is equal to capital T. That is what here we taken. From 0 to t will be is equal to t. So t into t. So that will be is equal to RC by t, where I square of t is nothing but this one. This one is nothing but this, right? C into Vc of t. You substitute over there, then we'll get. So here the one more important parameter is t, capital T here. Now we have to make an observation here, like if that t is equal to, first we can make that if this t is equal to RC, if I say, then your energy dissipation will be what? Then this will be 1 C into Vc square of t, means it is a conventional. If t is equal to RC, then it will be a conventional charging. Means energy dissipation will be C into Vd. That Vc is nothing but, you can say, example we can make the Vc of t is nothing but Vdd. So C into Vdd square. So if t is equal to RC, then it is a conventional charging. First. Second case, I'll go if the t is greater than RC, means twice times of RC, that is 2 RC we given. If this t is greater than 2 RC, means you can make it as like 2 RC, then what will happen? Then this will become as 1 by 2 CV square will happen. So the dissipated energy will be smaller than the conventional case, the previous case. Then here we can make the dissipation can be made arbitrarily small by further extending the charging time t. Because see, initially we made t is equal to RC, where R and t is nothing but a time constant, where tau is equal to RC. It's a time constant, where R and C is a time constant. Okay, it's a time constant. So now t is equal to RC, conventional. So t is greater than 2C. Now keep on increase the t. If t is greater than 2 RC, means if I take instead of 2 RC, if I make 3 RC, so automatically what happens? Still you can reduce the energy, right? The dissipation can be made arbitrarily small by further extending the charging time t. So means simple. Step by step we need to increase the time. That is the meaning. Very important here. What you need? Step by step we need to increase the time. So what we have to do in the sense, for that purpose only, we need to use a pieces is so like this, what is linearly you have to instance. This is your 0, this is your B, so that it tends to slowly we have to increase. So we can say that dissipated energy is proportional to the resistor, and a smaller resistor will result in lower dissipation, unlike the conventional cases. So what are the observation we can make it in the adiabatic circuits here? So the adiabatic circuits actually it will charge will be moves efficiently from power supply to the load capacitance by using a slow and constant current charging. Slow and constant current charging, that source we have to use. Next thing is reversing the current source will cause the energy to flow from the load capacitance back into power supply. So here this is what is it. So we need to reverse the current source will cause the energy to flow from the load capacitance back into the power supply. So that power supply must be designed. So if we want to do in that way, then we have to design a power supply to retrieve the energy fed back to it. So such type of power supply we need to design. So here this adiabatic switching circuits are required non-constant, non-standard power supply and with the time varying voltage, because in the previously the conventional method, the conventional CMOS circuits and all which used a fixed power supply only. Okay, we are not used very power supply actually. Fixed power supply only we use. It is a constant power supply we can say. It is a standard power supply. But here adiabatic switching circuit will require it's not a constant power supply and it also is not a standard power supply with the time varying voltage. A very important keyword here, time varying, like a ramp. So that supply only will be called as pulsed power supply. This is what we need to use. So here it will be like this. Your time now, see that you have to apply like this in this way. So this will be your time, charging time period, which get increases. It will get charges how much time. So you might, this is pulsed power supply we have to give instead of fixed power supply. So in the sense, instead of giving this type of power supply, example I am saying, right, we need to give the power supply like this. Simple. That is what we have to do. This is fixed. We can say this is fixed. This is not fixed or varying, we can say. Slowly we are varying. Here at the start 0 or VDD only. But here 0 start only VDD. You can gradually we can increase. This is about the adiabatic charging, the energy dissipation also we have seen. Then we made some of the observations also, like if the T is in this way. So now in this circuit now here which I have shown like this, in this actually what will happen in the sense the output of the power supply will be like this. See, okay, so what I will do, okay, yes, so in this place this will be a 0 volt as I mentioned. What about this? This will be your pre-charge, I can say. So during this time it will be pre-charge. What it will do here, it will hold. Then during this time it will recover. Then during this term here it will wait. This is what will happen actually in the varying time varying. So from 0 pre-charge, it will hold, recover, then wait for the next again to pre-charge. This is nothing but your the output waveform of a pulsed power supply. This only is output. Now what to do? Let us go for the first topic from the adiabatic amplification circuit. Let us study about the adiabatic amplified circuit. So this is the adiabatic amplification circuit which is mentioned over here. So what it will do this, so what is the amplification? The amplification, it is a fundamental operation which will be performed by electronic circuits to increase the current or voltage drive. So just remember, it's an amplification here. What we specify is you need to say it's an amplification. Amplification is a fundamental operation performed by electronic circuits to increase the current or voltage drive. This is the amplification. Now you can see here very important thing, the circuit, the symbol is this, okay, amplification symbol. Adiabatic symbol. Here you can see here it has, this is your input, this will be your output. So this adiabatic amplification, the circuit is consists of two transmission gate. This I can say the transmission gate number 1, that is TG1 I will call. This is I will call TG2, transmission gate 2. Next, two NMOS clamp is required. That is, these are the N1 and the N2 are two NMOS clamps. Now here you can see the input and outputs are dual railed. Dual railed means X bar, Y bar. We are having, right? That one we are calling as dual rail, means 0 logic 0 X 0, then the bar is 1. So I am having dual rail, or I can say VDD also. Then here same Y bar also I will get as 0 VDD. So here the inputs and outputs are dual railed, which is encoded to avoid the use of inverter. See, because the inverters will get only either 0 or 1. So to use of inverter, we can use the inputs and outputs are dual rail encoder. Now we can see this figure here. Let me take the operation. Okay, so let me draw the diagram first. First transmission gate, right? This will be your transmission gate. Next, one more transmission gate. Then we have a two clamp NMOS. So this will be your NMOS. This will be your NMOS. Okay, now we can say the inputs. So here the inputs and output. This will be the input as X. This will be the output Y bar. Then this will be your Y. Then this will be your X bar. Then this is the X bar. This is X. Then this will be your X bar. Then this will be X. So I'll make it as this will be a TG1, this TG2, then I'll make this as N1, this is N2. Then here we are having the input we need to apply. This is nothing but your VA. Okay, first step. So what we need to do first? We need to the input X and the complements are applied to circuit. First case 1, okay, the case 1 first, let me write as case 1 here. Operation inputs you are applying. First x is equal to 0 and x bar will be is equal to 1, we are applying. Okay, when we apply x is equal to 0 and x bar is equal to okay, x is equal to 0, let me say here x is equal to 0, then x bar will be is equal to 1, x is equal to 0, x bar will be is equal to 1, x will be is equal to 0, then x bar will be is equal to 1. Okay, so now what's happening here now when I do this, like what is this VA we need to know, right? What is this VA actually? The VA is nothing but it is a slow voltage ramp from 0 to VDD. It's very simple. If you want to say, the VA is like this. This is what 0 to VDD. This will be your VA. We are applying here. Okay, so yes, this is what we are applying. When you do that, okay, slowly we are applying. Just to think about from 0 to VDD. Now which one all is on? Let me write here. When x is equal to 0, what about the N1? N1 is off, correct? N1 is off. Next, what about N2? N2 is on. You need to think here in the output Y, here there is a capacitance. Okay, you assume as in this way. This capacitance, this side, this side. Okay, so now next, what about TG1 now? What about TG1 is on or off? X bar is 1, x is equal to 0, then TG1 is on. Because NMOS also on, PMOS also is on only. What about TG2? TG2 will be off. Now, if the TG2 is off, it won't pass. Because as we know that what is the, we have to make a note. What is the importance of the transmission gate? Can you tell me the difference between the NMOS pass transistor and the transmission gate? Pass transistor, any pass transistor. The difference between pass transistor and the transmission gate. Anyone? Where the pass transistors, the output will be degraded due to threshold voltage, because that is what we've seen previously. Like for NMOS, if I take, it can be able to produce like a good zeros, bad in ones. For PMOS, like passing characteristic, if I say it is good at passing 1 but weak in zeros. But what about the transmission gate? The transmission gate able to send the entire range of value from 0 to VDD without any degradation. That is the important characteristics of transmission gate. So now the transmission gate will be, it's a combination of the PMOS and the NMOS actually. So now here you can see the TG1, the NMOS, the X bar will be is equal to 1. This X is equal to 0 means the PMOS also will be on. Then the transmission is on. This will be off. So now what happened? So if it is off, because we are applying the slow voltage ramp from 0 to VDD, we are applying. When the TG1 is on, what will happen? The Y bar. So Y bar will be charging. Yes. So from this I can say the Y bar is charging. Correct? The Y bar is charging. What about the y? Doesn't have value. There is 0 only. The y is 0 because initially there is no charging in the value. So y will be is equal to 0. So I can say from this the circuit is energized. Here I can say circuit is energized, right? The circuit is energized passing. This is case 1. Then let me go for the case 2. What is the case 2 actually? We need to apply x will be is equal to 1. X is equal to 1 and x bar is equal to 0. Now you need to tell me what is n1 and what is n2. Then what will be tg1, then what will be tg2, then what about your y, that is y bar, then what about the y. So here in the sense simple I can say the y bar is charging in the sense capacitance is going from 0 to VDD, right? That is what meaning the capacitance. Now x is equal to 1. So let me put x is equal to 1. I'll apply. Now x is equal to 1. Now apply. So x bar will be is equal to 0. Then x is equal to 1. X bar will be is equal to 0. X is equal to 1. X bar will be is equal to 0. When I do this, now we are applied x is equal to 1 we applied. When x is equal to 1 in the sense now we see the n1 will be on. Yes, n1 is on. The n2 is off. Same come for tg1. So the x is equal to 1, x bar will be is equal to 0, right? So this is the second input. This is the first input. This is your second input. When x is equal to 1, then x bar is equal to 0. Then this tg1 will be off. So when the tg1 is off, tg1. So n1 is on, right? We have seen n1 is on, n2 is off. The tg1 is off. The tg2 will be on. You see this because x is equal to 1 means x is equal to 1. So this will be on. If this is on, here we are having the capacitance y. The portion of y will be charging. See, the y is charging. Y is charging from 0 to VDD. What about y bar now? Nothing is happening? No. The y bar is like what will happen? Already it was charged, correct? Already it was charged. Due to the x is equal to 1, the NMOS 1 is on. If this is on means there will be a dissipation from. So through the y will be y bar I can, sorry, this is y, right? Which is y? Yes, the y bar is discharging through N1, that is VDD to 0. See here I am getting the value, both complementary output I am getting. Y bar will be logically 1 VDD, y equal to 0. So second case I am getting y bar will be 0, y will be VDD. This is for both the plus sign. The circuit is energized. Now what we need to do after the charging is complete, note, we have to make it note clearly. Okay, this is the important note. After the charge is complete, this is charge is complete, the output signal pair, that is y on y bar, output signal pair remains stable. And it can be used for next stage. Used as input to the next stage. Okay, now we'll see. Now second thing is here I can say the amplifier is, or I can say the VA. The VA, if I do VDD to 0, so means the VA we are going to 0 actually, like this place, because we said this place it was charging, correct? This will be your hold, that is for stable. Next it will be recover. This portion is recover. That is the meaning of that. When VA is a VDD to 0, then it is very important. Earlier I said circuit is energized. Here the circuit is de-energized. Energized. The voltage from VA to 0 volt. So in this step, the very important thing what is there, the energy was stored here actually. The energy that was stored in the C, that capacitor. C is transferred back to power supply. That is a recovery circuit. So only we said it's a recovery. So that is why we need to design a power supply such like that the energy that was stored in C already. So when your power supply, that is your VS, goes back to 0, then again that whatever the energy was stored in the C, it will transfer back to the power supply. So there is no dissipation here when it goes back to your your voltage backs to 0. Not only is going to same, even it go back to negative 0. So now here this is the one of the very important thing. So now from this I can say the state of two transistor of the transmission gate, like the VA will be ramps up and down between 0 and VDD. Like the energy of dissipation, like if I can say like both the transistors both transistors operate in the non-saturation region. Non-saturation region in the middle part of the ramp actually. Middle part of the ramp pin up and down. That is how much the range, if I want to say, between VTP and VDD minus VTN, between this place. Because initially the NMOS will be on and it remains on till the output reaches the VDD minus VTH. So on the other hand, if you want to say, the PMOS will be turned on when the ramp voltage attains the voltage threshold voltage, and it will be remains on till the maximum value. So this is all about the adiabatic amplification. Here next what we need to study, we have to study about the adiabatic adiabatic amplification in like a full amplification, or we need to do some derivation, or let us do some portion of derivation about this. This is about the operation actually. Later we will study about how much the energy is stored in the load in this adiabatic amplification circuit. That we will calculate in the next class.